It's very easy to run a BLEVE case. I'm just going to go ahead and load a drawing for a BLEVE case. Let's load this drawing. And I've got here a geometry where we have, I'm going to just start off by excluding everything. And I'm going to now include the tank that we're interested in. So you could see that the tank is actually not very well drawn in this drawing. We are concerned with this tank in this case, and we're also concerned with these buildings here, this stair up to this staircase, include, and these buildings here, the shelter, some transformers, and I'm going to leave an opening in the tank. So I'm going to assume that the part that has ruptured in the tank is this part here, and so that's open. And from then on, it's just a matter of setting the scale, which we've looked at in other tutorials, right? So I can look at the dimension from here to here. That's 3.9. So we'll say 392 by 286, or 286 by 392. So it's width by height. So let's change that. 200. So it's 286 by 392. And so we've just multiplied the dimensions by 100. Assuming that the scale is 100, and we just want to get a feel for the length scale of this tank. So that's 0.2 times 100. That's 20 meters long, this bullet. So if the bullet is 20 meters long and it has a diameter of 7 meters, that's huge. Yeah. So according to the scale, the bullet is 20 meters long and has a diameter of 7 meters. So if it was a cylinder, so if it just go calculator, if it was a cylinder, what happened here? So it's 49.7 squared star a quarter, or pi over 4, 3.1415926. So that's 38 times 20, so that's 380, 760 really. Yeah, 760. Now let's say 770. That's the volume of the tank, 770 meters cubed. Okay, 770 meters cubed. Huge. Yeah. We'll take for this dimension here, and we'll take a tank. We'll put an ignition point in here, and actually we need to adjust the scale, so we can put let's say 1 by 1 meters. Let's see, yeah, it's good enough. 1 by 1 meters. So we can apply and close, and I'm gonna set. Let's redo this. Put the ignition point. We'll set the BLEVE parameters. So we set it 770. That's a meters cubed. The PSV, let's say it's 300 kilopascals, is the PSV setting. If this was a combustible material, we could, and if it was sitting in a congested area, we could model the fuel ignition after vessel rupture. And if all we have to do that is just click this setting, calculate the amount of fuel mass that's in there, put that in, and make sure that the surrounding area of the tank has the appropriate average pipe diameter and the average volume blockage ratio and the average confinement. But in this particular case, you can see that the tank is sitting in an open area, so it doesn't really. We're not gonna model that. We just need to set the custom gas cloud parameters here, and we're ready to go. So I'm going to set it off, and you can see that the pressure is about 3.6 absolute, which is 2.6, an overpressure of 2.6 bar. So once question is, how does that affect the rest of the domain? That's what we're going to look at now with the calculation. Calculation should be done very quickly, and we'll have a look at the results. Okay, so the calculation's finished, and we're going to load the results from this. I'm just going to click apply, and you could see the results at this stage. So we're looking at density. You can look at pressure. Of course, this is absolute pressure. If you want to output overpressure, you want to change this to you want to calculate that, so it's overpressure, so we change that to overpressure. We'll do it in pascals, and that's pressure with a capital P minus 101.325, apply, and we'll change the color scheme. Change the color scheme to DSAT. And we could just display the positive part of it, and you could see at this stage you've got a little bit of green, which is just under, it's 0.05 bar, but this is late in the day or late in the piece. So if we go say 20, it might get a higher pressure. Yes, in fact we've got like this is 0.15 bar at the edge of this. So any windows at this stage would be broken. If the building is not fortified, you'll have major structural damage. You could even have collapse. So it is quite a strong overpressure, large overpressure that's sitting there. Closer to the tank, if I go 15 here, for example, the pressure is higher. Of course, there's a velocity component, so you don't see that, but that's basically what you've got. And even closer at about 10, that is about really high, about 1.7. In a very within about 20 meters of the actual tank, the pressures are extremely high, but then they soon drop off as the sort of shock wave attenuates and expands into the open area. There is a slight pressure rise that you see due to the reflection of the shock, so you start to see a bit red here, so that's higher than 0.1 bar, so it's about 0.15 bar, and then finally at 27, that's the last calculation. We could have run it more, and it looks at the issue of the buildings behind. And you could create an animation. That's what we're going to do. We're going to create an animation. So, and that's very easy. You just select the folder, and you want to give it a name. And you run it, and it'll save it. This is normal. Requested resolution 944.755 been changed to 992.752 to match font or match format specification. This doesn't have a lot of frames, so it should be done very quickly, and then you'll be able to view the video. Here's how the explosion looks, expanding from the BLEVE and impinging on the wall of the buildings adjacent. That's basically it. And that's it. I hope that this clarifies how to carry out a BLEVE calculation. It is one of the easiest things to do. It's the state of the art. I don't think that there's any other software that has any sort of more detail than this. Of course, the calculation is in 2D, but you do want that conservatism in the calculation, so that's an advantage. If you have any questions, please feel free to contact us.